Hello, welcome back. This is Calculus by Dr. Oz. Today we're going to practice finding the interval of convergence of power series. Before we get started, I want to give you the definition of not only interval of convergence but also a radius of convergence. Here we go. When a power series centered at C is provided to us, you may fall into three different cases in terms of the convergence of the power series. The first case is that the series converges only at C. So it's just one point that the series converges, and all other points the series diverges. And in the second case, not only the series converges at C, but also within an interval where you can go r units far from the center to the left to the right, which means that the radius of convergence of the interval is of the power series is r. What that means again is that the series converges absolutely whenever the absolute value of x minus c is less than r, and diverges whenever you're outside that interval, which is absolute value of x minus c greater than r. And in the last case scenario, which could be the best case scenario, that the series converges absolutely for all x, and that's the case where the radius is infinity, because you can go to the left, to the right, infinitely many, like infinite units, essentially. So that's that you can cover the whole minus infinity and infinity interval. So that your interval of convergence is minus infinity and infinity. So in the first case, the series converging at only C, the radius of convergence is 0. In the second case, is just a finite number. In the last case, the radius of convergence is infinity. All right, so we have 4 exercises. Each of them is long. So I'm going to split this video into 4, and I will handle each case in different videos. All right, let's get started. All right, let's start with part A. When we have this analysis here, as I said, I will 99% of the time I will use the ratio test, and to find the interval of convergency, we should also include the endpoints when we come up with an interval. So this is like each sub question here is going to take long. So this will be in 4 consecutive videos. Okay, let's start with part A. So in part A, an is going to be 2x to the power of n. Remember, x is a variable, but we will use the ratio test. So I'm going to look at the limit of the ratio of the absolute value of the ratio an plus 1 over an plus 1 and an, right? So that is equal to 2x to the power of n plus 1 divided by 2x to the power of n. Okay, so let's simplify. So what I have here is 2x to the power of n times 2x divided by 2x to the power of n. Okay, and 2x to the power of n divided out. Okay, so I have the absolute value of 2x. Well, as I said, x is something that I'm going to peg along the way, so it's you can take it as like a number. So limit of a number is a number, so this limit value is going to be just 2x in the absolute value. And the ratio test says that if this limit is strictly less than 1, then it's convergent. The infinite series is convergent. Okay, so that means I'm going to choose x's in a way that x's satisfy this inequality. So let's check what that means. Well, the absolute value of 2x less than 1 means that 2x is in fact in between -1 and 1. By dividing everywhere by 2, you have -1/2 x and 1/2. So this is sort of like an immediate result that we get, that x's should belong to the interval -1/2 and 1/2. Okay. So now the question, remember in the statement, there was a warning saying that be sure to include a check for the convergence at the endpoints of the interval. So I'm going to sort of like analyze the endpoints separately here. So
So I'm going to plug in -1/2 in the first shot and check what the series look like and see if it's convergent. And I'm going to do the same thing for 1/2. All right, so if you plug in 1/2 in the description of the infinite series, so 2x is like 1, so you have 1 to the power of n. And if you plug in -1/2, it becomes -1 to the power of n. So these are two different infinite series. I'm going to check the convergency of those by using the applicable tests. So if you simplify this one, so any power of 1 is 1, so in particular, so you're talking about the series 1, and this is still the series -1 to the power of n. Okay? So here, you can take this as like a n equals 1. Okay? And this is an alternating series. So you have an alternating series. If you isolate the alternating part from the non-alternating part, so imagine like there's a hypothetical 1 here. So an equals 1. So for the first one, I'm going to apply the nth term test. For the second one, I'm going to apply the alternating series test for an to be 1. So for this one, so nth term test implies that since the limit of an, which is limit of 1, which is 1, is not equal to 0, so the nth term test implies that this is divergent. Okay, so it's a simple application of the nth term test, because you're adding 1 to itself infinitely many times. Obviously that sum is going to diverge to infinity. Okay, 1 plus 1, 2, 2 plus 1 is 3, you keep adding 1. In the alternating series case, an equals 1. Okay, you can check if the series is convergent. Remember the alternating series test. You have to have the limit of an to be 0 as one of the conditions. So in other words, limit of an, which is 1, had to be 0 for convergence, but it's not. So, so one of the conditions of the alternating series test is not fulfilled. Alternating series test. Okay, so that means this series is divergent as well. Okay, so let me just clean this here. So this is divergent to start with. And what did I use again? The alternating series test. So both cases are divergent. So I go back here that I do not need to put I don't need to put an equality sign for those inequalities. So I'm going to keep the interval that I originally had as is, because that's me putting the analysis for the endpoints in this slide, and both produce divergent series. So so the interval of convergency for part A is going to be -1 and 1. Okay, so -1 and 1, open interval. All right, so I'm going to start part B in the next video.